Thanks for watching. If you enjoyed this video, please hit the subscribe button and ring the notification bell so you never miss an update. Leave a comment below to help grow the channel, and don't forget to smash the like button. Lecture 88, water waves. So, water waves are actually particularly complicated, and we're not going to be able to derive the wave equation for water waves, but we can talk about it kind of phenomenologically, and then we're going to use a clever trick to find the wave speed for water waves in different circumstances, okay? So let's start with, what are water waves? Well, if I go out to a lake and I throw in a pebble, I'll see a ripple effect, right? That propagates outward from the center, right? You've all seen this, you know what I'm talking about, yes? And then of course we can think of the waves that we see at the beach, for example, right? Yes. So let's imagine that we're out in the open ocean somewhere and we just have some wave. Well, the distance between the one crest and the next crest, of course, is what we call the wavelength, right? And you might think, oh, well, then that must mean that water waves, since they seem to be going up here and they're down here, must be transverse waves, right? Yeah. Because it seems like the up and down motion is perpendicular to the direction of wave propagation, which is this way, let's say, okay? Okay. But you would be wrong to say that it's purely a transverse wave, because it's actually a mixture of longitudinal and transverse waves. So let me show you what's going on with the water at each point in the water wave, okay? So if we were to look at some water, like say a water molecule at the top of the crest, or at the crest, right? And we were to ask, well, what's the water doing here, right? It would actually be going this way, if the wave velocity is this way, okay? So it seems to be going this way, all right? And if I were to ask a similar question about what is the water molecule doing, say, at this phase of the wave, right, where this is right in between the trough and the crest, right? Yeah. So at this point here, the water molecule is headed straight down, okay? What's it doing at this point in the wave? Well, that water molecule is actually headed back in the other direction, you see? So we can think of the water going through a circle, right, where the radius of the circle is half of, it's equal to the amplitude of the wave, where the amplitude of the wave would be this orange line, which is where the water would be if there was no wave. That's just the level equilibrium surface of the water, right? That's its default position. When we have the wave, we'll have a crest which goes a distance a above that position and a distance a below that position, giving us the trough, right? Yes? So we can think of a circle whose diameter is equal to twice that amplitude, or one whose radius is equal to the amplitude, okay? And what's happening is the water is kind of going in a circle. So it's going a little bit up and down, but it's also going back and forth, you see? Because look at what it's doing. It starts out this way. Here it's going down. Here it's going back. Over here it's going back up again. And then when we're at the next crest, we're going in this direction again, you see? So we've gone a full circular path. You see that? So the water is kind of doing this circular motion, okay? Okay. So it's a combination of an up and down, right? Going from the low part, here it's down here, but you know, at a time later it's up here, right? So it's gone up and down, yes? Yes. But it's also gone as far over as here, and then back to this position here, where its equilibrium position was in the middle, let's say, okay? So it's going back and forth in a longitudinal fashion, and we'll talk more about longitudinal waves next time. We'll talk about pressure, right, in gases and things, okay? And those are longitudinal waves where the motion, the oscillatory motion, is in the same direction as the wave velocity. So if the wave is headed that way, the oscillatory motion is in that direction. So it's going back and forth like this, okay? As opposed to going up and down with the transverse wave, right? So does all of that make sense? And if you've ever been at the beach, right, you've probably observed this. You know, if you're a surfer, right, you're trying to ride a wave, you know, you've got to give yourself some kick, right, to accommodate for this, the fact that the water is flowing towards the crest that's behind you, right? So you've got to paddle to catch up, right? That way you can catch it on this part of the wave and ride it, all right? Okay. Now, I'm not a surfer, but I'm just kind of guessing at this, right? The reasoning behind what they do. You've seen them do it. Right? They get up, they paddle on their board, and then the wave arrives. They've got some velocity to counteract this, the fact that the water is actually moving in the opposite direction that they want to go, right? And then eventually they can stand up and kind of ride the wave. So they're always on this part where the water would be going. If we were to like pick it right here, the water is kind of, I'm not going to draw the circle, but it's kind of going like this, right? A little bit forward, a little bit down, right? Yeah. That's where they want to be. But we can actually do some numbers with this, okay? Because I've looked at a video of a wave moving across the frame at the beach and estimated the sizes, and so I'm going to use numbers that are easy to work with. If we assume that lambda, that's the distance from crest to crest or trough to trough, right? The wavelength, right? If we assume that that is 160 feet, okay? And that the amplitude, let me think here, what did I want to use? Yeah, 4 feet. We'll do 4 feet. if we let the amplitude be equal to 4 feet, right, so that means that from the undisturbed level of the water to the top of the crest will be 4 feet tall, you know. So call A equal to 4 feet. And if we were to watch this wave as it travels by, right, I can calculate by timing with a clock how long it takes for this crest to get from here to here, right? Just marking the position on the screen and the camera, right, and then seeing how many frames passed. If I know the frame rate, I can figure out the time, right? So I can determine that the time, we'll call it delta, we'll call it the period, is equal to 5 seconds. Okay? So do you remember the relationship for the wave speed in terms of the wavelength and the period? If I can measure the wavelength and the period of a wave, right, then I can tell what its velocity is, because it's just going to be lambda over t, right? Has the right unit, so that should assure us a little bit, right? Lambda is in meters, t is in seconds, meters per second is velocity, okay? So it seems reasonable to use, but I think we showed this previously, right? Where we talked about how the phase changes in a sine wave, right? Anyway, so what's that going to give us? That's going to give us 160 over 5. Who can divide 160 by 5?
32.
32, good. Not hard. 32 feet per second. That's the wave speed, right? That's how fast the wave is going by, right? Let's see how fast the water is moving, okay? In the picture that I showed, we have a circle, right, of radius 4 feet, right? And the water molecule starts here at the top, and then by the time it reaches the next peak, or the next crest, it has gone full circle, right? And travels back to the top again, right? So what is the distance that it traveled? Well, that's the circumference of this circle, right? And the circumference is 2 pi times the radius, in this case is the amplitude, right? So that's approximately 6, a little more than 6, times 4, which is the radius. 6 times 4 is about 24, but we'll say that it's approximately 25. That will make things easy, right? So the speed of the water, VW, is going to be equal to that distance that it traveled, which is the circumference. It traveled the full distance of this circle, right? And divide that by delta t, or by the period, the time that it took for to go from here to here. And that we know is, we'll call it t, and that's going to be 25 feet divided by 5 seconds. That gives us 5 feet per second. And isn't that interesting, right? The wave speed is considerably faster than the speed at which the water is moving, you see?
Yeah.
Because remember, the waves, right, transport energy and momentum, but not matter, right? Is there any matter being transported here? I may have been misleading you by saying that this water molecule went from here to here. What it really did is it stayed in place, and as the wave moved through, it went around this circle, right? This is the distance that it actually traveled here. It didn't go from here to here, right?
Yeah.
It traveled from here back to here again. So it basically is sitting still in place. It moves forward and then backwards and then back to the middle again, you see?
Yes.
Right? But it also goes up and down, and so that total path is this circular path that I've drawn here. Okay?
Okay.
So the speed that the water is moving is considerably less than the actual wave speed. So you're like, well, what's moving at that speed? Well, it's just energy transfer. Okay? That's the thing about waves. They transport energy and momentum, but not matter. Okay?
Okay.
All right. So now I want to try and figure out what is the speed of a water wave. And like I said before, this is a really complicated problem. It would be a great exercise in differential equations, specifically partial differential equations. If you get to that level of your education and you learn partial differential equations, then this is a nice problem to, cut your teeth on. Is that an expression? I don't know. It's a good problem to work on if you are trying to develop your partial differential equation skills. Okay. But I do not see any way to simplify it so that we can present it here. Instead, what we can do is we can say, well, if the amplitudes are small, it's going to obey the wave equation, okay? Like all waves. And we know that the wave equation tells us that, let me actually write it up here. Del to y, where y is any variable, over del t squared is equal to v squared times del to y over del x squared. Yes?
Yes.
This is that same wave equation we talked about the last couple of times. Let me go ahead and erase my pretty carefully drawn picture. So I want to use a technique that, as far as I know, the first time it was used was Isaac Newton. It may have been used before then. That's the first time I ever saw it used legitimately in physics. He used it to kind of affirm Boyle's law, which is a law that we'll learn about when we get to thermodynamics. But it's just called dimensional analysis, okay? And so it's a great way to guess at what the formula is. If you don't want to do it rigorously, maybe you just need the formula, okay? This would be very practically used in engineering, where you don't care how things come about. You just need equations that work. But we're going to do it here. But we need to first think, what are the important parameters that would go into a water wave? So what are the kind of things that might affect a water wave? So, well, that's what's, okay, I'm going to assume the water wave was made already. So we already have a water wave we want to describe, okay? But you're right, I mean, most water waves come about because of wind, okay? Other water waves may come about because of earthquakes underneath the ocean, right? These are what are responsible for the big tsunami waves that sometimes wreck coastlines. There are tidal forces, or waves are made by tidal forces. But yeah, wind is usually the culprit behind waves, okay? And it's a complicated process of little ripples giving rise to larger waves and so on and so forth, okay? But again, that's too much in the weeds for what I want to do here, okay? Here I'm going to assume I already got the wave formed, okay? And I want to know, how do I describe its properties, right? So wouldn't gravity affect it? We have water that's being lifted up, right?
Yes.
So that's going to require overcoming a gravitational potential, right? So we could say, well, gravity is in there. So we could say gravity. The wavelength, right? The behavior of the wave is probably somehow related to the wavelength of the wave, right? The wave speed. Maybe the amplitude of the wave. I'm putting the units here next to it. Meters per second squared. Another one that turns out to be relevant is the depth of the water. That's something measured in meters. What about the density of water, right? Density is a property of the material. Maybe we're talking about a methane or methane? Liquid methane. I guess you could have liquid methane. Methane ocean or something like that. But here we're talking about water oceans. So density would be kilograms per meters cubed. And one thing that can be relevant that we haven't even really talked about, we kind of talked about it. Remember when we talked about stress and strain, we talked about Young's modulus, right? And that was length over change in length, right?
Yeah.
And so we also have something called a bulk modulus. Well, that's not really where I wanted to go with that. Actually, yeah, sorry. The other component that we haven't talked about regarding liquids was surface tension. You notice how water will bead up on like a glass surface or something?
Yes.
And you're like, well, why doesn't it just like lay out flat and like evenly spread itself over the whole surface? So if I have a flat piece of glass and a raindrop falls on it, why doesn't the raindrop go out in every direction so that it evenly coats the surface of the glass with water molecules? It's because water molecules have a force, an affinity for each other, right? There's some electrical attraction between water molecules, which is causing them to bunch up into a little circle, okay? Now, when it's laying on the flat glass, it's of course going to be more like a pancake, right? Because you have gravity pulling down, yes?
Yeah.
And this is called surface tension, okay? And a good way to think about it, remember that when we talked about the pressure, so if I have a vessel filled with liquid, and we've got maybe one tube that goes up like this, and then another tube which goes up like this, but it's much fatter, right? And we said, well, in this case, the water level will be the same in both, right? Because the pressure is the same in both, yes?
Yeah.
I open them up to the environment here, right?
Yes.
Well, if I make this tube small enough, let me lower the level here a little bit. Let's say normally it would be here, but I allow this tube to be really narrow, right? It's a really narrow tube. You'll find that the water is actually higher in that tube. And the reason why is because of the surface tension component, okay? Because the little element of weight of the water there is small enough that its surface tension is enough to resist gravity and pull it up, okay? So if you look at like a cup or something, and when you fill it, let me see if I can draw this accurately. Here's a cup. And I fill it with some liquid. Oh, I really want to look at the side profile of this, so let me just draw it cross-sectional. The liquid doesn't go straight across the top of the cup if it's a narrow cup. Instead, what it does is it kind of dips like this, okay?
All right.
And we call that a meniscus, okay? Are you familiar with that? Have you seen that before? Next time you're using a measuring cup or something like that, have a look at the liquid in it, and you'll see that it's not flat across. It actually dips down, okay? a little bit like a chain hanging. Okay, it's like a catenary action. My guess would be it'd be described by the same curve, a hyperbolic cosine, but don't know that for a fact. It's just a suspicion. But it's because near the edges of the glass, the water molecules are attracted strongly to that glass. Okay, and it's kind of pulling itself up. Right, the water molecule is pulling on its neighboring water molecules through this surface tension effect. Okay.
All right.
We didn't talk about it because I didn't think it was all that important, but that's another effect that can affect these things. What are we going to use for that? Let's call it gamma. This is a lowercase gamma. And it has units of newtons per meter squared, the same as pressure, but you can, so because when we do this dimensional analysis, we're going to try to construct a formula for this velocity based on the units, so we want to use the same units. So there are no newtons up here, but we have kilograms, so I want to turn these newtons, right? Remember what a newton is? It's mass times acceleration, so it's kilograms times meters per second squared, right?
Yeah.
So I want to get rid of the newtons and put in the kilogram. Kilograms per second squared would be the units that it has. Okay? Yeah, looks good. And I can't think of any other major things that might affect a water wave. Okay?
Okay.
So when we do dimensional analysis, we can't really do it where we have the things that we think might go into the formula all have the same units, because then you can't really distinguish which is which. So we have three things here that have measurements of meters, okay? So we'll assume that we're in a really deep ocean so that the depth of the ocean doesn't matter, okay? So we'll get rid of that. I didn't tell you, but I should have when I had the picture up before, right, that these little circles you see, that effect actually decreases as you go deeper. By the time you get down to 1/2 the wavelength, the water's not moving at all, essentially, at that level. Okay, so it kind of subsides as you get deeper. So if the ocean is deeper than, say, the wavelength or so, then it's not going to really affect the water wave very much. Okay? Now, when it gets less than that, I mean, you've seen waves at the beach, and why are they coming in the way they are? Right? It's because as the bottom of the ocean is getting closer to the surface of the water, it's slowing the waves down at the bottom, right? It's causing them to basically bend and propagate straight for the beachfront. Right? That's why whenever you're on the beach, the waves always come straight in at you. But we're going to assume we're out in the deep water somewhere, so the bottom of the ocean is not going to affect the wave dynamics at all. So I'll get rid of that. And I think I'll also get rid of the amplitude, okay? Because we're going to assume that the amplitude is rather small, okay? So that the wave equation is valid, okay? So I'm going to ignore the amplitude. And so we're left with just these factors here, okay? And there are two regimes, right? So surface tension is not going to be very important if gravity is dominating things, okay? So I would say that if gravity is dominating things, right, then these two would be important. So these would be larger waves, what we might actually call a wave. If gravity is not all that influential, then I would say that this area here would be what we might call a ripple. So we call this ripples. These are really small waves, kind of like the things that you get when you drop a pebble in a pond. Yeah?
Yeah.
Because the amplitude is so small, right, and it's not being displaced very much gravitationally, it's not a huge mass, surface tension is playing a much stronger role there, you see?
Yeah.
Just like it is in the narrow-channeled tube, right? It allows the water to crawl up the pipe, right?
Yeah.
There the surface tension is strong because the element of water is a small mass, so the gravity is weaker, you see?
Yeah.
Yeah. Okay, and then this would be what we'd have, for waves. So we'll have proper waves and little ripples, the two kind of regimes we're going to look at. Okay? Let's do the ripples first, I guess. Okay? So how are we going to do this? We're going to say that the velocity is equal to the surface tension raised to the I power times the density raised to the j power times the wavelength raised to the k power, ijk. Okay?
Okay.
So those are our three parameters that I want to put in for this, okay? Now we're going to write down what are the units of velocity, and I'm going to write it like this. I'm going to write units of velocity are meters seconds to the minus 2. Yes?
Yeah.
What are the units of surface tension? I had just said it before. I said that it was equal to kilograms per second squared. So it'll be kilograms to the 1 times seconds to the minus 2. And that'll be raised to the I power. Okay?
All right.
Density has units of kilograms to the 1 times meters to the minus 3, raised to the j power. Yes? And wavelength has units of meters to the 1 times k, or raised to the k power. Okay? So we're trying to determine what are I, j, and k. All right?
All right.
So now let me use the law of exponents here and rewrite this. Meters to the second, meters to the 1 power, seconds to the minus 2 power equals, and then we'll mix all these up. We're going to have kg to the I times seconds to the minus 2I times kilograms to the j times meters to the minus 3j times meters to the k power. All right, now I'm going to collect all the terms together. Meters to the 1, seconds to the minus 2 equals, so kilograms to the I times kilograms to the j is kilograms to the I plus j power, right? Yes? If I multiply, x to the I times x to the j, that's equal to x to the I plus j, right? Law of x, it's just exponents, right? So I only have seconds in one case here, so that's times seconds to the minus 2I. And meters, I've got two things with meters in them, so that'll be times meters to the minus 3j plus k. We got everything? I think we do, right? So now we can determine what is I and j and k, right? Let's start with this one, seconds, right? Because we know that there's only one variable I in there, right? So we're going to have that s to the minus 2 has to be equal to s to the minus 2I, right? That's only going to be true if minus 2, so I'll write it here, seconds, seconds, minus 2 is equal to minus 2I. Wait, where did I get the minus 2I? Is that right? Ah, of course, confused. This is supposed to be minus 1. This is velocity, meters per second, right? Meters per second. All right, that clears up the confusion. So minus 1 equals minus 2I, right?
Yeah.
Well, that means that I is equal to 1/2, yes? Okay, so we have I. Let's see what else we can get. Let's look at the kilograms now, right? The kilograms tell us that, well, how many kilograms we have on the left-hand side, right? That's kg to the 0 power, right? Because there are no kilograms in velocity units, right?
Yes.
So we'll have kilograms to the 0 power, so that means that 0 is equal to I plus j. I plus j, which implies that I is equal to j minus j, right? Yes? That basically means since there's no kilograms on the left-hand side of this, on the right-hand side we must be dividing some quantity with kilograms by another quantity with kilograms so they cancel out, right? That's what's going on here. So I is equal to minus j. Well, we know what I is. That means that j is equal to minus 1/2. Okay? So we got one number left to find, k. And we'll get that from considering meters. And so the meters, we've got 1 on the left hand. So that means that k is equal to, we'll write it as 2/2 minus 3/2 equals minus 1/2. Okay? So now we have I, j, and k. So that means that our answer, right, the velocity is equal to the surface tension raised to the I power, well, that's 1/2, times the density raised to the j power, that's minus 1/2, times the wavelength raised to the k power, which is also minus 1/2. Okay? So what does that look like? Let's just rewrite it this way. It says that the wave velocity is equal to, this is for a ripple. I'm going to write it like this. I'll write this. Actually, I'm going to write it over here because we're going to keep it. V ripple is equal to, we've got a bunch of square roots here, right? So square root, this is a positive square root, so the surface tension is in the numerator, but both of these are in the denominator, over rho times lambda. Okay? So this is the wave velocity for ripples. Okay, and is it right? It is to a factor. There's a 2 pi that's not in here. We can't put in arbitrary constants. Dimensional analysis won't give us those. Okay, so there's always going to be some multiplicative factor that we won't have in our equation. But we could, of course, do an experiment and determine what that multiplicative constant is. Okay, and I forget exactly where it goes, but it's either in the denominator or in the numerator of this ratio here, and it's a factor of 2 pi that we're off by. Okay, but yes, that's essentially correct. Now let's look at the other case for real waves, not ripples. So now surface tension is irrelevant. Gravity is going to be dominating. Let's have a look at what we get. So we're going to have that the velocity is equal to g to the I power times rho to the j power times lambda to the k power. So I've really just switched out the surface tension component for the gravitational constant, okay? Is that what we call it, the gravitational constant, or is that big G? Well, you know, this little g is, 9.8 meters per second squared, right? And we're going to do exactly the same thing we did before, right? So we'll say meters times seconds to the minus 1 this time, mea culpa, is equal to gravity. We'll have units of meters per second squared, right? So I'm just going to kind of jump ahead here, right? This is going to be meters to the I, seconds to the minus 2I, right? Rho is, again, I can't put brackets around it, make it less confusing, is the density still. So that's kilograms to the J times meters to the minus 3J. And then wavelength is meters to the K. Okay? So now we just move everything together. That gives me meters to the I minus 3J. Seconds to the minus 2I. No, I messed something up. I forgot to put another term in. Sorry. We got this term here, plus K. Okay? Then we have seconds to the minus 2I, and then we have kilograms to the J. Okay? And over here we'll have kilograms to the 0, meters to the 1, seconds to the minus 1. Right?
Yeah.
Let's do kilograms first because we know where this is going. So kilograms tell us that 0 is equal to, so this is the 0. 0 equals, and we look at the kilograms over here, it must be equal to J. So that says J is 0. Okay?
Okay.
So there is no density term in this. This is gone. Okay? Rho to the 0 power is 1, right?
Yeah.
So density is not in this formula. We shouldn't have put it in there. Okay? Now we'll do seconds. That says, same thing it said before, it says minus 1 is equal to minus 2I, which implies that I is equal to 1/2. Okay? And finally, for meters, we'll get that 1 is equal to, because this is the 1, right? 1 is equal to I minus 3J, but remember J is 0, so that's nothing. Plus K, okay? Well, we already know I, that's 1/2, so that's 1/2 plus K. So that means that I is equal to, well, that's 1 minus 1/2, well, that's 1/2, right? I is equal to 1/2. And so now we have all the things that we need for this, right? This is equal to G to the I is 1/2, times rho to the 0, so we're not even going to put that in, times lambda to the 1/2. Okay?
Yeah.
Okay. Yeah, well, this should say K equals 1/2, sorry. K equals 1/2, instead of solving for K. Okay? And so that means that the velocity for a wave is equal to the square root again, because these are both factors of 1/2, but it's just G times lambda. Okay? And so these are the waves in two different regimes, right? If the wave is pretty large, right, then this will be the term that dominates it, right? I'm just curious what we would get if we used this on the wave that I got by looking at a video on the internet, right? So G is 32 feet per second squared. The wavelength was 160 feet, right? Let's see what we get. Who's got their calculator handy? Let's just calculate it for fun. Call it my wave. Also, it was kind of fudge. I made the numbers nice and round so that the division would be easy, right?
Yeah.
So let's see what we get. It's going to be the square root of G, which is 32 feet per second squared, times lambda was 160 feet. And then we're going to take the square root of that. Someone want to calculate that for me, see what we get? So
71.55.
71 feet per second. Okay, so that's about twice as fast as, a little more than twice as fast as what I came up with, okay?
All right.
But we can say it's on the same, I had a professor who used to always say, what's a factor of 2 among friends? And this was to, accommodate for his sloppy board work, because he would often leave factors of 2 and stuff like that out. So he would say that. But anyways, so what's a factor of 2 among friends, right? If we double 32, we get 64. That's almost 71 feet per second, so looks good, right?
Yeah.
Okay. But there's a 2 pi factor that should be in here. So hang on a second. Did I ever? Oh, I did. So I looked it up. So the real wave speed is actually a combination of both of these terms, okay? And it's written like this. The velocity squared is equal to G lambda over 2 pi plus gamma times 2 pi over lambda times rho. That's the actual wave speed that you would get if you were to do the hard math and come up with it, okay? We can still be in this regime though and say, well, this is small, right? If the amplitude is small, this will be insignificant, okay? I don't know, I don't see how directly, but anyways, I guess we could just say these numbers would be small. Certainly if the wavelength were small, this would be big. If the wavelength were large, this would actually be small, right? Here we have 160 feet, right? Here the 160 is in the numerator, here it's in the denominator, so it's making this term small. So let's ignore that term and use this. So we have to take this divided by 2 pi. What do we get then? Recalculate, please. 32, if you want to, I can make a quick simplification. 16 times 160 over pi divided by, then take the square root, please. I bet we get something close to what I estimated.
It's above the, I see, 28.50.
Cha-ching. What'd you get?
28.50.
28.5 feet per second. I came up with 32. Pretty good. That wasn't bad. That was a good estimation on my part. Okay, I think I hit it all. Okay, so that was the dimensional analysis that allowed us to come up with these two approximations for the wave velocity in these two different regimes. In the ripple regime, where the wave amplitude is small, the wavelengths would also be small, I guess. Okay, and in the regular kind of wave regime. All right, and we see that it's pretty close. And that's it. That's water waves, as much as we're going to talk about them anyways.
All right.
Sound good?
Yes.
All right. That's it.